All right, so let's take a look at this investigation. How much do we remember? So, how many words did we remember after 10 days? 10. 10 for 10. All right, and then 50 days, 8.6. And after a year, yeah, 6.2 or 6.109, something like that. Okay. So then it asks you to sketch a graph. So we've got number of words over here. I don't know why there's two S's on words, but apparently there are. And then these would be our days after learning. And what does it kind of look like when we graph it? We got 10, 10, 50, 8.6. And then these are just the points that we have over here that we got 365, 6.19. So maybe something like that. So when we graph, oops, too far. Okay, I'm just doing something like that. Okay. All right. Looks a lot like exponential decay. It went down really quickly and then it kind of leveled out. Just in terms of what we saw there, all right, on the graph. Okay. So let's do some description. Describe how the number of words remembered changes as time goes by. What's happening? Yeah, they remember less as time goes on. Looks like they forget a lot at the beginning. But they don't really forget them all. Okay. So how many words from the list does this model suggest someone would remember in the long run after many, many years? What do you think? About 6, okay? How do we know that? Yeah, looks like we've got an asymptote, all right? Looks like we've got a horizontal asymptote. At y equals 6, it just gets closer and closer to 6 the farther we go out. In fact, could we check it? Could we put in 2 years, right? So how many days that would be, 365 times 2, and see what we got, okay? So that's a possibility. So let's see if we can get this information from the equation itself. It says, describe the rate of change of the numerator and the denominator functions of w of t. So let's go back and let's look at that function. Here's that function, right here. So 0.4 plus 0.6t over 0.1t. Both pieces, if I look at them independently, are what kind of function? If I look at just the numerator, they're both linear, okay? So what's true about linear functions and their rate of change? Rate of change is just slope. Does slope change in a linear function? No. Okay, so they have constant slopes. And so if we look back over here, the rate of change of the numerator and the denominator functions are both constant. All right, they're both constant. And so it says which function, the numerator or the denominator, is growing faster. All right, so which one has a higher rate of change? The numerator does, okay? It's 0.6. All right, so we have the numerator. All right, its rate of change is 0.6. The denominator is 0.1. So it's growing 6 times faster. So what does this model suggest will happen to the number of words remembered as we get closer to 0 days? Yeah, it would get closer to infinity, okay? And so it would go over 50, right? It gets closer to infinity. It goes over 50. Is that a valid prediction? No, okay? So it's not very valid for the closer we get to time equal to 0, all right? It's very valid when we get farther out, but not quite as valid there at the very beginning, okay? So let's go back. I want to go back over here to your graph and talk about it for a second. It looked like we had a horizontal asymptote there. What do you think is probably happening there at t equals 0? What's happening right here? Yeah, there's a vertical asymptote right there. Okay, so we've got a vertical asymptote here. And then we've got this horizontal asymptote at 6. It's hard for me to draw that in. Okay. And so what I want us to do is just kind of formalize, what does it look like for a horizontal asymptote? How do we know that we have a horizontal asymptote? Okay. And so in order to do that, okay, we're looking at a couple of things. All right, we're looking at a couple of things. So proof of our horizontal asymptote. All right. We're basically talking about the end behavior of the function, all right, or the rate of change of the function, or our end behavior. Okay, our end behavior. All right, we know that the line y equals b is a horizontal asymptote, okay? If one of two things happens. If the limit as x approaches positive infinity, knocks on the door.
Hi, friends. Thank you.
Oh, and you got Starbies.
Oh my god, that's so embarrassing. I went to the little office. I didn't realize the sign-in's in there.
Oh,
That was not fun.
okay, it's okay. We're glad you're here. Oh, and here's the well, no, I put it back there. Okay. The limit as x approaches infinity of the function is equal to that number b. Okay. Or the limit as x approaches negative infinity of that function equals b. Okay. The key here is we have to check both limits. So last year, we found the horizontal asymptote, and then we talked about what it was doing. What was the limit as x approached infinity? Well, today now we look at it backwards, all right? We start with the limits and see, did I get the same thing each way? Right? So I want to go back to our investigation here for just a second and talk about what those limits would look like. How would we know if we take this original function that they gave me, how would we know as x approached infinity that we're getting this value b, all right, that we're getting 6, all right, each time? Is your notability staying or going? Is it still flashing in?
iPad's just dead.
Oh, okay.
I think it's back open.
Okay. And there's an operating system update for your iPads. If you've not installed it, be sure you do that at some point, okay? You've got to have at least 20% battery, I think, for it to work. You don't have to do it right now, but I know there's been a software update that's come out, so be sure to check and keep it up to date. I'm not sure that'll fix all the issues we've been having, but, you know, that's what they told us in an email. And every time I get an email from that guy, I want to punch him in the throat, but it's okay. Okay. All right, so let's take a look. Our function that we had for w of t, I'm just going to write it back up here, was 4 plus 0.6t over 0.1t. Okay. And so when we get ready to do these limits, the limit as x approaches infinity, what I'm going to do is the end behavior. So what would be the highest degree? I guess we should put t there because we're talking about t. What would be the highest degree term of the numerator? Or what, there's only one thing with the variable there. It'd be that 0.6t. All right. Of the denominator, it'd be our 0.1t. If we simplified that, what's going to happen to the t's? They're going to reduce out, okay? Because right now, you know, it's not really helping me. So if I take the limit as t approaches infinity of 0.6 over 0.1, that's a constant. It's 6, okay? So that's how we can justify that we have a horizontal asymptote there. Based on the nature of this function, do we need to think about approaching negative infinity because of what this function represents? Can we go backwards in time? No, we don't have a flux capacitor. So we cannot go backwards in time. So I just made a joke. Y'all don't, did you get it? Back to the future, yay! Snaps for you. Okay. My husband just ordered all 3 movies, by the way, on DVD or Blu-ray. I can't remember. Anyway, I'm like, why? Why? It's okay. It's like all Rebecca's going to do is sell these when we die. She's not going to care about any of these DVDs. Okay. All right. All right, so that's what we'll check. So let's take a look at what some of our questions are going to look like, okay? How do we find a horizontal asymptote? How do we prove that we have a horizontal asymptote? They love these questions, all right? I pulled this one from AP Classroom, all right? It says, so 3 rational functions are shown. Determine for which functions the graph will have a horizontal asymptote, all right? So let's take a look at the first one. So I have, let me zoom in there, x squared plus 3x minus 28 over 2x squared minus 14, okay? What would be the end behavior of that function? Because I can consolidate this a little bit if I do it. What's the highest degree term of the numerator? Yep, x squared. And what's the highest degree term of the denominator? That 2x squared. That will simplify. What does it simplify to? 1/2, okay? So now I can take the limit as x approaches infinity of just a 1/2, which would just be what? Limit of a constant is a constant, okay? We could go the other direction because I'm not doing anything in context this time, okay? So if I do the limit as x approaches negative infinity of 1/2, what's it going to be? 1/2. So we have a horizontal asymptote at y equals 1/2. Okay, so 1 cha-ching has a horizontal asymptote. All right. Let's take a look at the second one. Okay, what would be your end behavior model of g of x? 3x cubed over x cubed, which would just simplify to just 3, okay? And so if we take the limit as x approaches infinity of 3, it's 3. The limit as x approaches negative infinity of 3, it's still 3. So we have one horizontal asymptote at y equals 3. Okay, so the second one works. Okay, then let's repeat that process for the third one. What would be your end behavior model of h of x? X squared over x, which would simplify to just x. And so now if I take the limit as x approaches infinity of x, okay, direct substitution says I'm going to plug in what I'm substituting, all right? So if I plug in infinity, what would I get? Infinity, so I don't get a number, okay? If I do negative infinity, same thing, right? So is there a horizontal asymptote to that third one? No, okay? it has to equal a number, right? It has to equal a number. And so my answer would be C. Okay. Question about that? All right, or how we check for horizontal asymptote. Right. Let's look at this next one. Y'all try that one. Which functions do we have a horizontal asymptote? Okay, it is multiple choice, so you don't have to show all your work, which is nice. Okay, so let's see, what do we think? Which one has a horizontal asymptote? Or which ones? Two, okay. I hear 2 and 3. I heard 2. All right, let's look at them. So if I look at the first one, my end behavior, if that's all I start with, would be 3x cubed over 2x squared, which would simplify to 3 over 2x. If I approach infinity with that, 3/2 times infinity is just more infinity, okay? So I'm not going to get a horizontal asymptote there for sure, okay? Let's look at the second one. If we look at our end behavior model, that's going to give me x squared over x to the third, which would be 1 over x. Now think about that. 1 over infinity, what's that going to get really, really close to? If I have 1/5, then I have 1/10, it gets really close to 0. Okay, so this one, the limit as x approaches infinity of 1 over x will be 0. So you will have a horizontal asymptote at y equals 0. Remember that, okay? A constant over infinity is going to get close to 0. All right, we're just getting a smaller and smaller fraction. Okay, with the second one, or the third one, what's tricky about it is they rearrange the order. Your highest degree term of the numerator is 3x to the 4th over x squared, which would leave me with 3x squared. And if I think about that, 3 times infinity squared is a whole lot of infinity. Okay, so it's not a number. So the only one that works is 2 right there. They did that on purpose with that third one. All right, so that your eye was immediately drawn to that x squared over x squared, and you forget to look at that 3x to the fourth in that numerator. Okay, they do that mess. All right, so just be careful there. So question about the horizontal asymptote piece. Okay, now what's nice is this also applies to if they just want me to evaluate a limit at infinity. Okay, we're not really thinking about the horizontal asymptote, we're just thinking about the behavior of the function. Okay, just the behavior of the function. So I want to look at this first one, okay, and think about what my end behavior might be. Okay, so I'm going to actually evaluate this by taking the limit as x approaches infinity. Again, we're not looking for a horizontal asymptote, we're just evaluating a limit. Okay. What's the highest degree term in the numerator? 9x to the 6th. It also happens to be under a radical, and that's okay. So the square root of 9x to the 6th. Okay, that's my highest degree term. What's my highest degree term in the denominator? 4x cubed. Okay, now let's think for just a little bit. If I take the limit as x approaches infinity, square root of 9 will give me what? 3. Square root of x to the 6th. Not 4th. X to the 3rd. Okay, x to the 3rd. If you think about it, 6 x's, I pull them out in pairs, there would be 3 pairs. Okay, so the square root of x to the 6th is x to the 3rd. Right? As if I had x times x times x times x times x. 1, 2, 3, 4, 5, 6. There are 2 pairs underneath the square root. 3 pairs underneath the square root. All right, so that's why I can pull it out as x cubed. Okay, my denominator is 4x cubed. Oh, what's going to happen to those x cubes? They cancel out, and what's my limit equal? 3/4. Okay, so we can evaluate that limit for infinity just like we would with an end behavior, which is nice. Okay, let's look at the second one, because I think this one's interesting too. All right, highest degree term of the numerator, or leading function, would be that 2 to the x. Okay, what would be the function in the denominator? 5 to the x. Okay, 5 to the x. And so if we think about that, one way to look at it, because they both have an exponent of x, I could rewrite that as the limit as x approaches infinity of 2/5 all raised to the x power. Okay, that's 2/5 all raised to the x power. What's going to happen if I take 2/5 to the infinity power? What's going to happen to that fraction? Is it going to get bigger or smaller? Smaller, so that whole limit's going to approach what? 0. Another way to think about that, who grows faster, 2 to the x or 5 to the x? Like if you graphed it, who would grow quicker? The 5 to the x, okay? So because the bottom's growing faster than the top, it will approach 0. All right, so another way to think about that. All right, what do we think so far? Okay, what I want to do is to rework that question A in this problem and look for horizontal asymptotes. All right, because something interesting happens when we talk about horizontal asymptotes. All right, if I'm just evaluating the limit as x approaches infinity, it's pretty straightforward. Okay, but if I want to find horizontal asymptotes, it's going to require a little bit more work from me. Okay, and the reason why is because of that end behavior model. Okay, because when I take a square root, all right, how many options do I really get if I were solving with a square root? I'd get 2, right? A positive and a negative. And so when we think about for horizontal asymptotes, because we're going to have to approach negative infinity, we're going to have to approach positive infinity. When we do the square root of 9x to the 6th, we have to write that as the absolute value of 3x to the 3rd. Okay, for that top part. the numerator will still be my 4x to the third. Okay. And the reason we do that is because I have to think about the limit as x approaches positive infinity and the limit as x approaches negative infinity for horizontal asymptotes. Okay, so only have to do this when I'm looking for a horizontal asymptote. On the positive side, I want the positive absolute value, so it would be what we did a few minutes ago, 3x to the third over 4x cubed. That would go away, and so I get a horizontal asymptote of y equals 3/4. Any guesses about what's going to happen on the negative side? Yep, because of that piecewise definition of absolute value, we're going to have negative 3x to the third over 4x to the third, which would give me a negative 3/4. So we actually have two horizontal asymptotes in this problem. Okay, and so I just wanted to show you that. The only time we have to consider that is for a horizontal asymptote. Okay, if we take a square root, when we're looking for a horizontal asymptote, we've got to put it in absolute value because we're going to have a positive and a negative because of the situation. Okay, otherwise it's good. I just wanted to show you the difference between those two procedures. All right. Last and worst. Okay, last and worst of infinity limits is coming up with this next one. Right. When I look at this one, first of all, there's multiple functions being multiplied together, okay? And one of them's not even a single denominator, like it's just craziness, right? So if we want to do this, the limit as we approach positive infinity, the limit as we approach negative infinity. In order to get our end behavior model, we got to get it to one function up there. Okay, so we got to do a little bit of work. We're going to do some algebra to start. Right. I'm going to leave that second parenthesis alone because it is, okay, one singular rational function. But that first one is not. Okay, that first one is not. I need a common denominator. 2 has nothing, so what would its common denominator be? X plus 1. If I put it on the bottom, I got to put it on the top. Okay. Minus my x over x plus 1. I'm going to continue to simplify, leaving that second parenthesis alone. Right. Now we're going to be able to keep a singular x plus 1 in my denominator. And on the top, I'd have 2x plus 2 minus an x. Okay, so I'm just getting this down to a singular function and a singular function. So that would leave me x plus 2, and then everything else would stay the same. An x plus 1, an x squared, and a 5 plus x squared. So just some good algebra here. We're going to distribute. So that's going to leave me x cubed plus 2x squared. In the denominator, I'm going to have 5x plus x cubed plus 5 plus x squared. All right. Don't have to put it in standard form. Just need to be sure I've got all my like terms combined. Okay. So we had to do the algebra on the front end so that I could do the calculus on the back end. All right. So now we want to do our two limits. The limit as x approaches infinity. We can use the end behavior model. It tells me what happens on the end of the function. What's the highest degree term of the numerator? X to the third, and of the denominator. X to the third, what's that going to reduce to? 1. Okay. Does not matter that I'm approaching negative infinity. I have the same end behavior, x cubed over x cubed, which would be 1. Okay. So do the algebra on the front end. Make it one function. Okay. Fair enough. Just a little algebra for you right there. All right, let's talk about vertical asymptotes. Okay. So vertical asymptotes. All right, so our vertical asymptotes happen where the denominator is undefined. Okay, so if we're going to prove a vertical asymptote, these are the things we have to look at. Okay, the line x equals a is a vertical asymptote. If the limit as x approaches a from the left of f of x gives me positive or negative infinity, or the limit as x approaches a from the right of f of x gives me positive or negative infinity. So that's how we prove it. Right? We approach the value that we think is the asymptote. Does it give me positive or negative infinity? Okay. Now, one of the things that they will ask you to do is to describe the behavior around a vertical asymptote, and they'll ask you to do it without a calculator. Okay. In order for us to do that, we have to plug in values to the function, so the entire function, on the left and right of the asymptote. Okay, so you remember we did a lot of that testing of values. All right, so for asymptotes at 1, we might want to check 1.5 or 1.2, and we might want to check 0.5 or 0.8, okay, around 1. So plug in values to the function on the left and right of the asymptote, okay? If you get a positive answer, it implies positive infinity. If you get a negative answer, it implies negative infinity in terms of the behavior. Okay. I wonder if they hit the wall over there or something. Or maybe just my refrigerator idled off. I don't know. It's a little scary. Okay. Well, it is almost spooky season. Yeah, when it hits September, I put my spooky stuff out. I've still got my 4th of July stuff out right now. We're still patriotic at my house right now. Okay. All right, so is there a function that we know about that we use that has a vertical asymptote that isn't rational, okay? This is one we have to remember, and it's just one of those things that we don't think about a whole lot, okay? Anybody, can you think of one? It's our logarithmic function, right? Log functions have vertical asymptotes, okay? Because exponential functions have horizontal asymptotes. They're inverses of each other, so things switch. So something like y equals ln of x, y equals log base 2 of x, okay? If we graph those, remember log functions do this thing where they cross the x-axis at 1, and they have that vertical asymptote, okay? So just as a reminder, all right, you will get a vertical asymptote anytime you're asked about a logarithmic function, all right? But most of our functions we're going to look at are rational. okay, because we know about wholes and we know about asymptotes and all that good stuff, okay? So let's look at a couple of examples and then we'll be almost done. Okay. So, which of the following has a vertical asymptote at x equals 3? Okay, so let's just take a look at these functions. We don't have to show all the limits. We're just thinking through this for a second. Which ones would have an asymptote at x equals 3? What about the first one? Would it have a vertical asymptote at x equals 3? Yes. Why? Yeah, the denominator would equal 0 if I plugged in 3. So this is a yes. Okay. What about the second one? It has a hole. Okay. So if it has a hole, that's not a vertical asymptote. So this is no because it's a hole. All right. What about the next one? Yes or no? Nope, it's a hole again, all right? I have the same factor in the numerator as I do in the denominator, so that's a hole as well. Okay, what about the last one? That's a yes, okay? Because I have more in the denominator than I do in the numerator, okay? So this one is a yes. There's a vertical asymptote because if I reduce that, I would still have an x minus 3 in that denominator, okay? So those have vertical asymptotes, all right? Question about that? Okay, let's look at the next one. Oh, goodness. Okay, so here's my function. X squared and all that stuff over x squared minus 4 times the natural log of the absolute value of x minus 4. There's a lot going on right here. Okay, there's a lot going on right here. All right. One thing that I need to notice is that I've got a logarithmic function. It will always have a vertical asymptote, okay? It will always have a vertical asymptote. It's going to be the opposite of whatever is in parentheses. So where's that asymptote going to occur? At 4, okay? So we're going to have a vertical asymptote at x equals 4 because I'm multiplying by a logarithmic function, okay? Always. But now let's talk about that rational function that's there. How are we going to know if they're wholes or if they're asymptotes? You got to factor. Okay, so factor your numerator. X minus 2, x minus 1. And your denominator, x minus 2, x plus 2. Okay. Are we going to have a hole for this one? Yeah, the hole is going to be at x equals 2, so that will not be a vertical asymptote. And where will the vertical asymptote be? At x equals negative 2. So I'm looking for negative 2 and positive 4, which would be C. Okay. All right, last couple of examples. Okay. What do you think on 11? All right, this falls into that interpreting, mathematical language into mathematical symbols. The values of k of x can be made arbitrarily large. Anytime you see that word arbitrarily, chances are it's a limit, okay? Because we like that word, what's associated with limits. All right, so arbitrarily large by taking x sufficiently close to 7 but not equal to 7. Which of the following statements must be true? It is multiple choice, so which one do we think is correct? D, okay? It would be D, all right? X is getting close to 7. That's the kicker, okay? Meaning the function k of x is getting close to infinity or arbitrarily large, so it would have to be D, okay? That word arbitrarily to me takes out the first two options. Then you got a 50-50 shot. Okay? So there we are. All right. So this is part of that section 9 that I didn't teach, like multiple representations. This is what it's talking about. Okay? Then let's look at this next one. So it's known that the limit as x approaches -6 of the function is negative infinity. Okay? So as it approaches -6, notice it doesn't have to the left or to the right. So what does that mean has to be true? It's got to approach negative infinity on both sides of 6. And so if I look at my tables, they all split down the middle. That means on each side, I got to have, of that line, I need a really big negative number. Okay? Which one's going to give me that on both sides? A. Okay? Again, a multiple representation. Understanding the limit, using a table to do so. All right? Okay, one last thing we need to put on our reference sheet, okay? You know we had that limit as x approaches 0 of sine x over x, okay? Well, here's one for when x approaches infinity of sine x over x, all right? So I want to think for just a second. You remember when we did the squeeze theorem, the limit, okay? I could separate this as 1 over x times the sine of x. And if you remember, every time we did that, we bounded our function, our trig function, by that function at the front, okay? We used x squared, so we had a positive x squared and a negative x squared. So I want you to think for a second, all right? What would be one of my boundary functions if it's 1 over x out there? Okay, if one of them is 1 over x, what's the other one going to be? Yep, negative 1 over x. It's the opposite. So remember, 1 over x looks like this. Okay, in diagonal quadrants, guess what negative 1 over x does? The other diagonal quadrants. Okay, and the actual graph is sine of x squeezed between all of that. Okay, so if we think of sine, it starts at 0, it goes up and then down and up and then down and then up and then down and then up and then down and up and then down, all between that, okay? Same thing on the other side. Okay, so as we approach infinity, what is that boundary of 1 over x going to do to that sine function? Squeezes it down to what? 0. Okay, squeezes it down to 0. So the value of this limit is 0. Add that to your reference sheet. It comes from the damp trig functions. For most of us, it's just easier to memorize that bad boy versus, okay, trying to remember the squeeze theorem. Okay, but that's where it comes from. So that may show up in some of your calculations. You can use it. If at some point you have the limit as x approaches infinity of sine x over x, we know that's equal to 0. Okay, and then we can just mess with what's left. All right. Okay, cool beans. Well, here's your lesson practice for this. This lesson will not be on the quiz. This is what will be on your quiz on Thursday. Okay, so on page 80, we're going to do 3, 8, 16, 22, 24, 25, 29, 30, 41, 42, and 55. Okay, you do have a wrap-up today on Google Classroom. All right, so let's get that taken care of. All right, quiz tomorrow. All right, 1, 8 through 13. So that was our squeeze theorem, and then all that stuff we did on Thursday and Friday of last week. That right now I can't remember off the top of my head. Okay. And tomorrow after this quiz will be a good time to do your retake as well. Okay, so you should probably have enough time to do both in class tomorrow, those of you that want to do your retake. But that's due by Wednesday.